So now let's apply friction to screw threads and see what we can learn about the behavior of screw threads. And so when we're done with the lecture today, you should be able to determine the required moment on a screw thread in order to accomplish a goal, either tightening the screw or loosening the screw, or even whether the screw can be back driven or not. There are several parts to this, but primarily we're going to look at the analysis of screw threads. So here's an application where we have a turnbuckle, and the screw threads are used to provide tension in a rod. So as you turn this turnbuckle, you'll notice that the screw threads on either side are right-handed and left-handed. It's a pair. And so when you turn the turnbuckle one way, it pulls the 2 points together. When you turn the other way, it releases. And so how do we determine the amount of tension, or how the tension relates to the turn of the screw thread? How do we look at that? And how do we know how much torque is required, or how much moment, if you will, is required in order to turn the turnbuckle itself in order to loosen or tighten the tension in the rod? How does the frictional force relate to the moment and to the force, the load in the rod, which will often given the symbol W? How do we relate all of this together? And by the way, if we apply this, will it loosen on its own? Is there some way that it could just backdrive? If the load is hard enough, is it possible that that load could cause the turnbuckle to just spin off? That's a good question. We can analyze this with statics and determine answers to all of these questions. So to analyze screw thread, we have to understand what it really is. You can think of a thread from a screw as an inclined plane. You could unwrap one rotation, one thread, one complete revolution of the thread, and lay it out flat and look at it, and it would just look like an inclined plane. Now, obviously, there are multiple inclined planes, and the nut, whatever part is the nut, interfaces or contacts multiple threads. So you could unroll this as long as you like. This is just a helix of thread that could be unrolled and laid out flat, but let's unroll one revolution of the thread. If we do that, we'll be able to see what's called the lead length of the screw. That's given the symbol L. The lead length is something pretty simple. If you've ever worked with a fastener or any type of screw, when you rotate that screw by one complete revolution, the amount of advancement of the nut or the screw in or out of the thread, that distance is the lead. It's most fasteners, which is what people are used to. Most fasteners are single helix fasteners. They have one single thread. Now, when you get into linear motion with Acme thread and square thread, they usually also are single start, or in other words, they have one single helix thread around a mandrel or rod. But it is possible in linear motion to have multiple helixes that turn around the rod all at the same time. In that case, the lead and the distance between adjacent threads is a different thing. The so-called pitch is different from the lead. But for 99% of the cases out there, and certainly for just about all fasteners, the lead and the pitch of the thread is the same. In other words, the distance between, say, the crest of each thread is simply the lead. It's the pitch. It's the distance between adjacent threads. So you can see that lead by unwrapping one revolution of the thread. You can also see a base, which would simply be from geometry 2 pi r, because of course 2 r would be the diameter, and then pi times the diameter would be the circumference of this thread. So that's the base of this triangle, and it's just a right triangle. And this right triangle is formed and has a so-called lead angle, theta, that you can see. And the whole concept is just unwrapping one single screw thread. Now, of course, because there is some thickness of the thread, we've got to decide at what point on the thread we're talking about. Don't worry about that detail. Just pretend for now that the thread is infinitesimally thin. It's close enough for what we're doing. We're just trying to get a crude model of screw thread that we can analyze. And like I said, in reality, there are multiple threads that are engaged, but we're going to pretend that, there's just one thread or just one. Well, actually, we're going to act like it's a box moving up an incline. And this is not a perfect model. In fact, if you do finite element analysis or you get in depth in analyzing screw thread, what you find is there is variation in the amount of load that's distributed amongst the various threads. And in fact, once you get deep enough into the length of the thread, that thread takes practically no load. But for our purposes, this will be close enough and will give us some general understanding of how screw thread works and some concepts that will help us with them. So we're going to model it as if the nut thread is just a box being moved up or down an incline. In this particular case, we're applying torque to the screw thread itself in order to push up, to push against the load. Notice that in our simple example here, our weight is acting downward. It's trying to prevent the screw thread from coming up, but the moment or the torque that we're applying to turn the thread is moving against the load. So when we say upward motion in the context of screw thread, what we mean is that the nut or the screw is moving in a direction that the load does not want it to move. Okay, so that's upward motion. It can be upside down and literally be moving down, but as long as it's moving opposite the load, we call that upward motion. So we've made a free body diagram of this little box that we're trying to push up the incline that represents the nut thread or screw thread. It doesn't really matter. But notice that the amount of force being applied to push this box up would be the moment we're applying this torque divided by the radius of the screw thread. Now, of course, the load is acting downward, trying to prevent this motion from happening, and there will be some friction between the screw thread and the nut thread, and there will be some normal force, normal to the incline. Now, we're going to combine this friction force and normal force into a resultant R that is shown as a blue arrow because it's easier to conceptualize and understand if we do that. Now, the friction force itself is equal to the friction coefficient times the normal force in this case, because notice we're qualifying this and saying this is upward impinging motion. It turns out that you will have static friction between the nut and the screw thread as you apply more and more torque to get it to start moving. You've got to overcome static friction, and that's the point we're analyzing. After the screw thread starts to turn or the nut starts to turn, it's actually easier because then you have kinetic friction, but we're going to deal with just static friction, and notice static friction is what must be overcome in order to cause motion. So our maximum frictional force at any point, as we're saying, we've got a wrench on this thing, we're starting to turn it, our maximum frictional force will occur right when the screw thread starts to move. And so that's why we say that the frictional force is equal to the friction coefficient multiplied by the normal force. However, notice we could rearrange this and write the friction force over the normal force, just solving for the friction coefficient, but just from geometry, that's equal to the tangent of an angle. What is this angle? Well, this is called the angle of static friction. Okay, it's phi sub s, it's the angle of static friction, and all it really does is tells us how much friction there is versus normal force, what percentage of the normal force. It's a stand-in, if you will, for the friction coefficient. So that angle is useful, and it's easier to work with the resultant of the friction force and the normal force rather than the two separately. So that's what we will do, incorporating in the angle of static friction, phi sub s. So now if we sum forces in the horizontal direction, as you see according to the axes there, the x direction, we know that for statics, right before this thing starts moving, we know that the sum of the forces must be equal to 0. Now obviously the friction and the normal force both provide some negative x or negative horizontal direction force that resists the motion that we're trying to impart to the screw thread or the nut thread, whichever the case may be. But notice it's easier to deal with the resultant of the friction and normal force, and so that's what we've got in the equation there. So there's really the friction and normal force combined that's resisting the moment divided by the radius, which represents the force that we're trying to apply to push this, push these threads so that they move relative to one another. Now notice that since we need to get to the coordinate system, the vertical horizontal coordinate system, we need the lead angle theta, but we also need the angle of static friction, phi sub s. So we simply add the two together and of course take the sine of that angle in order to get the component of the resultant that's in the horizontal direction. We can also sum forces in the vertical direction, the y direction. In that case, all we have is weight acting down and a component of the resultant of the friction and normal force acting upward, and you can see how we've come up with that in our equation as well. Now you can rearrange the equations a little bit, divide one by the other, and what will happen is the resultant will cancel out. Now, of course, you can combine the sine and cosine function into a tangent function, rearrange a little more, and what you end up with is an equation that allows you to calculate the amount of torque required, or the moment required, that must be applied to either the screw or the nut in order, well, I guess technically to both, in order to make the screw thread move up against the load. So this is the torque required to tighten the thread, or to move against the load. And this is really important. Now, be careful. Some printings of the book have this and many other things that I'm going to show you confused. So be really careful. You should open your book to the page that talks about all of this and correct it so that it matches what I have here, because what I've got on these slides is correct. Some printings of the book have various errors. I don't know how they came about. You might search for errata for your particular edition of the text and see if there's a file out there somewhere that's been published that talks about all the various errors in the book. And this one in particular is pretty bad in some printings of the book. But what I've got here is correct, and you can use it. What about self-locking? What do we mean by self-locking? Well, a thread could be back driven by the load that it's clamping, or the weight that it's supporting, if we apply no moment and if the friction is not adequate to prevent that. So now we're at a point where the friction force is less than or equal to mu n. Remember, that's our original equation. And we can still rearrange this and talk about it in terms of an angle, but the tangent of that angle has to be less than the friction coefficient, because there's only so much friction. So that angle phi sub s, the angle of static friction, can only go so far from normal. Okay. Now, if there's enough friction, if there's adequate amount, then what that means is that the angle of static friction can be equal to the lead angle. And if that happens, then notice that the normal force plus the friction force is exactly offsetting the weight. Now, remember, there's no moment being applied here. Despite my picture there, we're not applying it, or you could say that moment is equal to zero. And our question is, will the weight cause the threads to back drive? That's really the question. Well, if we have adequate friction, then the angle of static friction will be equal to the lead angle, or it can reach the lead angle. And our sum of forces, obviously in the horizontal direction, is zero because there would be none. Our sum of forces in the y direction means that the resultant, the sum of the normal and the friction force, would offset the weight exactly and prevent motion. And so that's desirable for many applications. But what about if it's not self-locking? In other words, what if the friction coefficient is too small? In other words, yeah, we've got some friction, but we can't actually turn the resultant far enough because the friction is not large enough to resist it. Then what we've got is something that can be back driven by the load or by the clamping force, and we require some torque in order to prevent that from happening, in order to accomplish a static equilibrium. So let's sum forces in the horizontal direction. Again, notice now the sine function needs the angle between vertical and the resultant, and that angle is the difference between the lead angle and the angle of static friction. And summing forces in the y direction, similarly, both the resultant and the weight appear in this equation as well. But of course we need the cosine function to take the component of the resultant that is vertical. We can combine these two again the way we've did before, and I haven't shown you the algebra here, but here's the result. And what is this thing? Well, this equation, m prime, tells us how much torque is required to prevent the load back driving the screw thread. Okay, so this is how much you'd have to hold just to prevent it from loosening up. Okay, so this is another important equation. Note it's a little different than the equations we had before. Same terms, different order, different way of calculating, because of course what's happening is the resultant vector is moving around, and so our equations have to follow it. Now, what about if we've got a thread that is self-locking and we want to back it off? What if we want to move downward, in other words, with the load? Okay, relieving the load or relieving the clamping force. Well, in that case, notice that we have to fight friction, because there's so much friction that as we start to try and slide downward, friction acts opposite of that impending motion. And this is just before it starts to loosen up, obviously. It's impending motion. So the friction is acting to prevent us from loosening. So this is a self-locking thread that requires some torque to back out the thread. Now, if we sum forces in the horizontal direction, notice our moment now has to be in the opposite direction, so that, and you can see that in the picture, so that the thread moves in the direction that the weight wants the thread to move. In other words, in the direction of the weight or the clamping load. And notice that we've got an m double prime over r, and I forgot the double prime in my equation, but anyway, it's that single prime should be a double prime. I just forgot to make the change. But I did put the directions correct. So we've got negative m double prime over r plus the component of the resultant that acts in the horizontal direction. And you can see how the angles there, since the static friction angle is larger than the lead angle, we have to take the difference between the two in order to get a proper sine function out of it. We can also sum forces in the y direction at similar argument, and then put them together to come up with the amount of moment required in order to loosen the thread. So this would be like you're unthreading a screw. So there's the torque required, m double prime, in order to move the load downward or to release the clamping load in a screw thread. Now these equations are not perfect, okay? There are more complicated equations. If you take my machine elements class, we'll discuss them then. But this is a sort of a first order approximation model, a reasonable model of screw thread that can help you understand how screw thread works and, you know, distinguish the various behaviors of screw thread, where they can be self-locking or non-self-locking, and so you can see from the equations why more torque is required to tighten a load than is required to loosen the load, because as you loosen a load, as you loosen a screw, the load itself applied to the screw helps in loosening the load. So there's a different amount of torque required in both. And another thing that this model illustrates is the fact that when there is no motion, then you've got static friction, and therefore more torque required in both the torquing and untorquing, the tightening and loosening of a screw thread. Now these equations are also important if you're talking about linear motion. If you're using a square thread rod or a Acme thread or some other thread form, a buttress thread for example, these equations apply, or modifications of them apply, and similar concepts and thoughts are important there, where we're unwrapping a screw thread and we're thinking about the friction that's acting and how it helps when we're moving, or I'm sorry, the weight or clamping load helps when we're trying to loosen, whereas friction resists in both cases. And of course, without adequate friction, the screw thread can be back driven, which can be a problem in some cases, but an advantage in others. It just depends on the application.